Last week we learned about the chain rule, and everything that we did last week was chain rule and only chain rule. Now we're taking the chain rule and we're going to be combining it along with all of our other rules that we have. So really we're going to be doing a lot of combination work today now. Just being able to know which rules are we using when and all that kind of stuff. All right, so let's go ahead and take a look at finding this first derivative now. So do I need to do anything to this one, like reformatting wise, before I go and start taking the derivative? Or can I take the derivative from here? What do you think? Yeah, I'm inclined to leave it as it is for doing this. We can distribute in, but we really don't need to here. It's not going to gain us anything. In fact, it might even make it a little bit harder. So if I'm going to find the derivative here, which rule am I going to be using? And actually, just so you know, I'm going to be asking that question a lot today. When I talk about which rule, there's tons of these little rules that we're using, but I'm mainly focusing on product rule, quotient rule, and chain rule today. So as we talk about which rule we're using on any given problem, that's what I'm talking about, because like a lot of them will use power rule or whatever like that as well. So which of those rules will I need here? Will I need product rule? Well, do I have multiplication taking place? Yes. So yeah, we're going to need some product rule then. Are we going to need quotient rule for this one? Is there division taking place? No, no division, no quotient rule. Do we need chain rule for this one? Well, do we have a function inside of another function anywhere here? No, we don't actually, because this e is to the power of theta. Theta works just like x does. It's just our variable, right? So it's going to be e to the theta. There's no extra function there. It's just the theta. Inside of tangent, it's just a theta. And so because of that, you don't need to worry about using chain rule. All right, so then we know that we're going to use product rule then. So we're going to go g prime of theta equals product rule, original times derivative, right? So we're going to do original e to the power of theta times the derivative. What's the derivative of tangent? So yes, that's going to be secant squared of theta there, minus the derivative of theta. What's the derivative of theta? 1. Because of course that's just 1 theta, right? So that's going to be the same as like if it was the derivative of 1x, it's just 1. All right. Now, are we done? No. And the thing is that sometimes we think we are because we just did that derivative, but of course we're using product rule here, right? So it's going to be plus derivative times original. And I'm going to jump down to the next line here since I'm running out of room. So derivative of the original, derivative of e to the theta, it is just e to the theta. That's the great thing about those e to the power of functions. They're their own derivative. And then it's times original. So the tangent theta minus theta just stays exactly the same. All right. If you wanted to, we could actually like try distributing in the e to the thetas or factoring that out of every term. But I'm going to go ahead and just call this good right here. We don't need to do any additional manipulation here, and it's not going to like gain us anything. There's no like terms that would end up being able to combine. So we're just going to go ahead and call this done right here. Then on to the next one. Please find this derivative. All right, so there are 2 different ways you could approach this particular problem. The first way is that you could first rewrite the original equation as y equals cosine of theta squared, just to make it a little bit easier to see, plus sine of theta squared. And then we could use chain rule there. And so we could go y equals 2 cosine theta times the derivative of cosine, which is negative sine theta, plus 2 times sine theta cosine theta. Because we're using chain rule there, right? And then, well, that gives me y equals negative 2 sine theta cosine theta plus 2 sine theta cosine theta. And then we simplify it. And what does that simplify down to? Well, notice it's the same thing, just one's positive, one's negative. They're opposites that we're adding together, so the whole thing equals 0. And so yes, this derivative equals 0. And what was the easier way to be able to get there? Because I said there were 2 ways to do it. What else could you have done first instead of doing this? You could have just made the whole thing equal 1. Because, of course, this is our most useful trig identity, right? Sine squared plus cosine squared equals 1. And if I had started by saying that the whole thing just was y equals 1, then I could go straight to y prime equaling 0. Now, either method, as you will see, as you saw here, does work. I would hope that you would do the simplify first, though, because, of course, that's going to make your life a whole lot easier, right? Now, this one, no, there's not a nice way to simplify it through. So we got to actually find our derivative on this one here. Which rules are we going to use here? Are we going to use product rule in this case? Are we going to use quotient rule? Are we going to use chain rule? Well, oftentimes it's a question of product rule or chain rule. This one is product rule because the sign here is being multiplied by cosine. It's not inside of cosine, so you should be using product rule as you go through it. All right, so we're going to have to do original times derivative, so the original cosine of theta times the derivative of sine, which is cosine of theta, plus derivative times original. So the derivative of cosine is negative sine, and then that's going to be times sine theta. And then we just need to clean that up a little bit here. So we got y prime equals cosine squared theta. And then it was a minus, because it was a negative sign there, sine squared theta. Can that simplify now? It doesn't really equal anything special. This does not equal 1 because it's a minus, not a plus. And so just stop there. Just give your answer there as cosine squared minus sine squared. And now we're really going to start mixing up the rules even a little bit more, because we started off with product rule mainly because I wanted to make sure product rule is still fresh. Bringing it back. But for this one, are we going to need product rule here? Well, to answer that, we look through, do you see any places where you're multiplying 2 functions together? Well, am I doing that here? Is that multiplying those 2 functions? No, it's not what the parentheses there means, right? That e to the t is inside of sine. It's not times sine. Now, what about over here? Is that multiplying the 2 functions? No. Again, that sine is inside of the e to the power of. And so, no. So no product rule in this case. And I know every now and then somebody sees the plus because there's a plus in our final result from product rule, and they think maybe that would suggest product rule, but remember, the plus is just separating it up into individual terms. We take the derivative of each term separately. All right, would I need quotient rule here? Well, do you see any division? No. So definitely not quotient rule. Chain rule. Do we need chain rule in this case? Yeah. We're definitely going to need chain rule here. So let's go ahead and use that here. So go ahead and find the derivative now on your own first, and then we'll do it together. All right, so as we start going through this one then, for f prime of t then, we got to do our chain rule on just the first term. So I'm only doing the first term at the moment. So we're going to do derivative of the outer. So that's going to be sine. What's the derivative of sine? Cosine, positive cosine, yep. Cosine of the exact same thing, right? So it's going to be cosine of e to the power of t. But then we have to multiply that by the derivative of that inner function. What's the derivative of e to the t? Well, it's just itself, yeah, so it's e to the t. That term is now done. That's that derivative. Again, using chain rule there. So derivative of the outer times derivative of the inner. All right, now then, on to our next part. We got to do chain rule again. So we're going to do the derivative of e to the power of sine of t. Well, the derivative of e to the power of anything, of course, is just itself. So it's going to be e to the sine t. The difference is, though, that we're not done here because it's not e to the t, it's e to the sine of t. So I still have to multiply it by the derivative of that sine of t. And the derivative of sine of t, of course, is cosine of t. And outside of maybe just doing a little bit of cleanup in terms of reordering or something like that, this one's done. So this is all we needed to do here, because notice there's no like terms there, there's nothing we can combine, no other simplification we can apply to that, so you're done there. Now again, let's talk about which rules we might need to use here out of those big three. Will we need product rule in this case? Yeah, we do actually have some multiplication taking place between two functions here. That multiplication symbol would be right here in between our two sets of parentheses, right? And so we are going to need product rule. Now, are we going to need quotient rule? No, definitely no quotient rule, right? Because no division. Will we need chain rule? Yes, or at least with what I would consider to be the preferred method for doing this, we would need chain rule. Because we can really look at it as having this as the inner function for that first side, and this is our inner function for that second side of that equation. And so within our product rule, we're going to be using chain rule as well. So make sure that you're including both of those phases. Now I said the preferred method because technically, yes, you could actually try multiplying it all out, but who really wants to do that, right? It's much easier to just go ahead and use our rules as we have them. So let's go ahead and start working those through since you've already gotten this one done, hopefully. So we can go straight to our derivative, g prime of x equals. So remember we're doing product rule here. The chain rule is really within the product because we really have these two parts that are being multiplied. And when we're multiplying those two, it's the chain rule within them that we need to worry about. And so the product rule is kind of the outer rule, the first one, the umbrella rule that everything else is going to be under. So I'm starting off by thinking of product rule here. So that's going to be original times derivative. So the original, the x squared plus 1 cubed, that part stays the same. Now that is going to be multiplied by the derivative of the second one. And so let's again do a little bit of coloring on these just to kind of keep them straight. All right, so we're not going to do the derivative of that. That's what I'm missing. So then that's going to be times, I got to use power rule on the outside. The inside stays the same, remember. Then that's to the power of fifth, but then we multiply that. Okay, I want to color code that here. We multiply that by the derivative of the inner function. That's what allows us to do it, of course. So the derivative of x squared is 2x. The derivative of 2 is 0, so that goes away. So that's the original times derivative. Now we're going to do plus derivative times original. And so that means I have to do the derivative now of this part over here. And yes, that means doing chain rule there. So I'm going to be doing the derivative there, so that's going to give me 3 times the x squared plus 1 squared. So that's the derivative of the outer, but then I multiply that by the derivative of the inner. So the derivative of the x squared plus 1 is again 2x. And then that's going to be then times original, because that was, remember, let's see here, make sure we got it all straight. We did original times derivative plus derivative times, so what's missing is original. So it's this original right here that we still got to fill in. And so it is original, so it just stays exactly the same. And there, that's done. Now in this case, I really do want to clean it up at least a little bit because it drives me crazy, at least personally speaking, when I see stuff like this 6 sitting in the middle there. And so I at least want to like pull those integer values out front, all that kind of stuff. So if I do that, I would also grab the 2x out of this first one. So the 6 and the 2x, I can combine those nicely and easily there. So that's going to give me a 12x. And then x squared plus 1 cubed, x squared plus 2 to the 5th. I just like doing that little bit of cleanup. And then we could do the same thing on that last one where I can multiply the 3 by the 2x. So that's going to give me 6x. Then x squared plus 1 squared times x squared plus 2 to the 6th. Now, could we clean it up even more from this? Well, it depends on what you mean by cleaning up. There's other manipulation you could do. If you really wanted to, you could try factoring out a 6x out of each term. Heck, you could even factor out a x squared plus 1 squared and an x squared plus 2 to the 5th out of every term. But I'm just not worried about doing that here because that's not really going to gain us anything in the long run. So I'm just not going to worry about it. I'm going to go ahead and leave it like this. Even in terms of that, leaving it here even would have been okay. It just bugs me when we got numbers sitting in the middle like that. All right, so let's start strategizing here. Now, first of all, you actually have some options in this one. Are we going to need product rule in this case? I think most people would say yes here, but not everybody. Are we going to need quotient rule with this one? Most people would say no, but a couple people end up saying yes on this one, and I'll show you why here in a moment. Are we going to need chain rule? Yes. Now, I was saying it's a little bit iffy. Do we want to use product rule or quotient rule? Either would actually work. It'd be one or the other, but you could actually do either. And because if you really wanted to, you could rewrite this at the start as cosine of 4t over e to the 2t. Because I know some of you, you've been so well trained at seeing those negative exponents that as soon as you see that negative exponent, you want to go ahead and put it into the denominator here like this. And if you want to do it that way, you can. Which one do you find easier, product rule or quotient rule? Your answer to that question is the rule that you should use in this case. Because since you have a choice, choose the one you prefer. Now, personally, I prefer product rule. So I'm going to do this using the product rule here. So I'm going to just see it as the multiplication taking place right here. So then, when we talk product rule then, really what I'm doing is I'm going to be doing original times derivative plus derivative times original like this. So knowing that we're going to be using product rule, think about how you're doing that and start setting it up. I know some of you are having trouble getting started on this one, but start by setting up what would go where in terms of product rule. Now, if we were looking at doing this back to our original rule, if I just wrote it in terms of the original rule, we got y prime equals fg prime plus f prime g, original times derivative plus derivative times original. If I were writing it this way, that would mean that I'd be calling this function f, and I'd be calling this function g. So in terms of lining up what goes where, that's how we're going to be approaching it. And if you find yourself having trouble with some of these where there's multiple rules going on within the other rules, that sort of thing, this is a great approach. Is to start by writing out the general rule in its most general terms and then start filling in from there. Otherwise, we find ourselves trying to keep track of too many things in our head at the same moment. All right, so we're going to go y prime equals. First of all, f, that's original. So it's that original first part, just that e to the power of negative 2t. And that's going to be times the derivative of g. So that's going to be now the derivative of cosine of 4t. Well, what's the derivative of cosine? Negative sine, yeah. So this is going to be times a negative sine. And which rule am I currently using now to do the derivative of cosine of 4t? Since we got that 4t on the inside, what do we call that rule? Chain rule, absolutely. So I'm having to use chain rule here. So it's going to be sine of the 4t, but then I got to multiply it by the derivative of the 4t. And of course the derivative of 4t is what? That's 4. All right. So that is the original times derivative part. So now we're on to doing the plus. All right, so now for that second part, we're going to be doing derivative times original. So we start by doing f prime, so that's going to be the derivative of e to the negative 2t. Well, the derivative of e to the power of anything is itself, of course, right? But because we do have that inner function, we will do e to the negative 2t here, but then we have to multiply it by the derivative of the negative 2t. And what is the derivative of negative 2t? Yeah, that's going to be negative 2. All right, and then, so that's the f prime. So now we're going to multiply that by g, the original. So the second one goes in exactly as it was. It's going unchanged. So that's just 4t there. And there's our derivative. And again, we could try cleaning it up. We can do some simplification, yes. But this is our derivative. This is the main part that I'm worried about you being able to find. This is the most important step. Now, if you did simplify it, this is what that might look like. And I say might because, of course, it depends on what the purposes of simplifying would be and what all that would be gaining you. Because, like, you'll notice that if you wanted to, you could actually factor a negative 2e to the negative 2t out. And you could do some stuff that way. But again, I'm not worrying about doing that step because it doesn't look like it's going to get us anything special. So stopping here is just fine. Then we're just going to be doing one more of these together before I let you loose to doing a few on your own here. So go ahead and write down this one and start planning out which rules are you going to need to use for doing this problem. All right, so before we start working it through, let's again plot and scheme which rules are we going to actually have to use here. Product rule. Will we need to use product rule in this case? Yeah, I think most people are going to say no to product rule on this one, but I say most people because it's not strictly speaking, and I'll show you why it doesn't have to be a no there. What about quotient rule? Do you think we're going to need quotient rule on this one? Well, I do see the division taking place, and yeah, I see a number of you nodding. So that division there is telling me, yeah, I'm probably going to end up needing to use quotient rule here. And finally, what about chain rule? Will we need chain rule here? All right, and chain rule, yeah, I would say chain rule would be necessary here because you got that function inside the square root, and so we'll definitely need it for there. Now, we were talking about product rule versus quotient rule. Either one can technically work here, but if you were going to try to use product rule, you'd have to rewrite the inside the square root as s squared plus 1 times s squared plus 4 to the power of what? That would actually have to be a negative, yeah, because inside of our square root, we'd have to show that part was on the bottom. So you could have rewritten it this way and used product rule. And you might be thinking, well, shouldn't I do that then? Because I think the product rule is easier than quotient rule. Kind of, but you'll notice you actually just created another chain rule within the chain rule kind of a situation. So yes, you can do it with product rule, but you'll have to use chain rule an additional time, so you might prefer not to. So I am going to stick with using quotient rule on this. Now, if we are going to find the derivative of this big original function, of course, the first thing I want to do and need to do is I need to be thinking about the square root. And square root, of course, is the same as to the power of 1/2. So I'm going to write that whole thing as just to the power of 1/2. And then I can go ahead and start using chain rule and quotient rule. Now, which one am I starting using here? Am I starting with chain rule or am I starting with quotient rule? That's then the next question. Well, do I have the function within the function, is that inside of the fraction, or is the fraction inside of the other function? So, like, let's actually kind of highlight it, kind of see where that would be. So, if I were going to look at where the function within the function is, my inner function is that. It's the fraction, right? Now, since my inner function is the fraction, it's going to be finding that part of the derivative where I'm going to need to use the quotient rule. So the very first thing I'm going to be using is actually the chain rule. So chain rule comes first here, and then you're going to go and get into using the quotient rule in order to execute chain rule. So start by using chain rule here. So for that chain rule part, that first step of chain rule, it would just be like finding the derivative of x to the 1/2, for instance. right? I know there's a lot more complicated stuff going on, but it's the same basic idea, right? So when we do derivative of x to the 1/2, that gives us 1/2 x to the negative 1/2, right? The difference is that in this case, it's not an x. It's that big old fraction. Well, that's okay. We're going to work with that, right? So it's going to be that same fraction, just the 1/2 is out front. That fraction's on the inside, so s squared plus 1 over s squared plus 4 to the power of negative 1/2. So that's the derivative of that outer function. Same way as what we did when we were taking a look at just this over here. The only difference is that instead of it being just plain old x on the inside, it's a function, so that means I have to now do it times the derivative of that inner function. And the derivative of that fraction means quotient rule. So inside of this last parenthesis that you're putting in here, you are now writing quotient rule. All right, so when we go to start using quotient rule, remember, low d high minus high d low all over square what's below. So low, that's going to be the s squared plus 4, d high. So the derivative of s squared plus 1, that'll be 2s. Minus, so that's high d low, so that's going to be the s squared plus 1 times the derivative of the bottom. Derivative of s squared is 2s, and that's all over the square of what's below. So that's going to be all over the s squared plus 4 squared. There we go. We have our derivative. Can we clean it up from here? Yes, you can. I kind of don't want to, though, because I'm just going to like blow up your brain a little bit, because we're going to have this fraction inside the square root that's going to be inside of the other fraction and some other stuff, so I'm just not going to worry about that right now. I want to make sure we can get to this point since we're combining those multiple methods. So just as long as you can get this, you're in good shape.